Okay. I think people should be joining now. So hopefully there's someone out there and they can hear me. You're welcome to speak up in the chat if you can, and then we'll know for sure. But I'll start anyway. So welcome everyone to this IOP talk tonight. It's our first time using Teams, so hopefully everyone has managed to log in, or some people have managed to log in and are hearing this. Very excited this evening to have our speaker, Chiara Marletto, speaking to us tonight about the physics of can and can't. So I'm going to hand over to her in just a second, but just to remind you, please, can you put in questions as we go through the talk in the Q&A button, which you should be able to see there. And I will pass them on to Chiara at the end of the talk. So, yep, great. There's some people answering. They can hear me. Fantastic. So, without further ado, I'll hand over to Chiara. Chiara is a research fellow at Wolfson College in Oxford. And she is giving us a talk tonight, as you can see, Beyond Quantum Computation, the Physics of Can and Can't. Over to you, Chiara.
Thank you very much. Hello, everyone. It's very nice to be here with you. So I will give you an overview of a very new and exciting area of theoretical physics that has also implications for the quantum theory of computation, therefore for computer science, mathematics, and even philosophy. So this should be very, very exciting evening. So I'll start with quantum computing. So I think we've all heard about this field that appears to be right now like an engineering enterprise. So you might have seen in the news the fact that there's a race between tech giants like Google, Microsoft, and others trying to realize what we call a universal quantum computer, which is an upgraded version of the computers that we currently use, because it will run on quantum effects, and when it's realized, it will allow us to perform algorithms that classical computers can't perform, and that can attain this famous quantum supremacy. Now, the engineering technological aspect of the universal quantum computer is, of course, of great interest, but I think that's not the direction I'll be heading towards. I will rather stay on the foundational side of things, because one thing that perhaps not many people know is that the universal quantum computer was proposed as an attempt to understand better the foundations of one of our most fundamental theories of physical reality, which is quantum theory, and specifically to understand the implications that the quantum effects have on information processing and on measurement. So I'll go ahead and say that quantum computation as it is now is an unfinished revolution. So I like to call it like this because in the first place, it's a revolution because it brought the idea that things like computers, which appear to be macroscopic emergent objects, are actually very important for the foundations of physics. And in fact, by studying computer that can run on the laws of quantum theory, we realized that we could understand quantum theory much better. And therefore, all the phenomena that quantum theory allows, like entanglement and superposition and so on, all of these phenomena have become much more and better understood over the past 20 years since the theory of quantum computation has been proposed. But the theory of quantum computation is an unfinished revolution because it completely relies on the laws that quantum theory runs on. So it relies completely on the Schrödinger equation, which is like this law of motion that quantum objects obey. And in this sense, it's a bit problematic because we know that quantum theory, as it is now, will have to be modified to incorporate other aspects of physical reality, notably gravity. So gravity is a classical entity which is described by the other most fundamental theory of physical reality that we have, which is general relativity, as was proposed by Einstein about a century ago. And gravity is classical. It doesn't have quantum effects, and it wouldn't be able to support something like a quantum computer. So when these two theories will be merged together, we'll get a different theory, which isn't quantum theory. And the question remains somewhat open as to whether we'll be able to define a generalized idea of a quantum computer, even in this new theory, where we are leaving behind all of the machinery of quantum theory itself. But we might be we might be left with still effects like entanglement and superpositions and so on. So that's one reason why we need to go beyond the quantum theory of computation. The other reason is that, surprisingly, the universal computer is not the most universal machine one can think of. Now, the universal computer was proposed by Alan Turing as a programmable computer that can perform all computations that are physically allowed. And then David Deutsch, who's a British physicist working here in Oxford, among others, suggested the possibility of upgrading this universal machine to including quantum effects, and that's the universal quantum computer. But there are tasks, transformations, that a universal computer is not able to perform. And one important task is the task of constructing a copy of itself from elementary materials. So this is a task that we know is physically possible because it's implemented by objects like cells. They can self-reproduce. But unfortunately, we can't program our computer to create a replica of itself. That would be very nice, but we can't. And we can't not just because our computer is not designed properly, but because the most fundamental theoretical scheme behind a computer that was the one put forward by Turing doesn't allow the programmable machine to perform this task. And this is why a great mathematician and physicist called John von Neumann invented a new type of machine. So he thought of a machine that he called the universal constructor, not computer, which is a programmable machine that can perform any transformation, any task that is allowed by the laws of physics. So you can think of it as a bit like as a kind of universal 3D printer, which, among other things, if it's permitted by the laws of physics, is also capable of constructing a replica of itself. And this is very interesting because it gives us an idea to go beyond the quantum theory of computation in a different direction, not by trying to incorporate theories that are not quantum theory, which was the first type of generalization I mentioned, but by trying to incorporate machines that are not computers, incorporate constructors. Okay, so to answer this question, how do we generalize the quantum theory of computation to incorporate constructors and also to go beyond the laws of quantum theory? We need to go on a detour, and we need to take a look at how physics formulates its laws, and then we will consider a very interesting step forward. So if you consider the way in which physics has formulated laws of nature so far, you can see that there are at least 4 great, formidable guesses that we have put forward. Newton's laws, so classical mechanics, Maxwell's equations, which is the classical theory of light, and then, as I said, general relativity and quantum theory. Now, all of these laws appear to be very different from each other. The first 3 I mentioned are classical, they don't support quantum effects, quantum theory has quantum effects, etc. But in fact, they are very similar in one important respect. And this is the fact that they use dynamical laws, so laws of motion, that describe trajectories of objects in space and time, given an initial state. So it's a bit like when you want to predict the trajectory of a football, starting with an initial velocity and position. Now, you can do this with the Newton's laws, but if you were to try to describe a quantum object by using quantum theory's laws of motion, you would be doing exactly the same thing. You would be solving equations and describing what happens to the object in space and time, given some initial conditions. And the idea is that the most fundamental explanations for the universe have got to be cast in this form. However, there is actually much more in the universe that we inhabit than what this mode of explanation can express exactly. So I'll give you a few examples. So there are things like the properties of living beings, phenomena like natural selection, and the emergence of a particular kind of information that's resilient, and it's the thing that powers living systems and our civilization as well, which we can call knowledge, which are compatible with the microscopic description of atoms composing all of these organisms that compose the biosphere, for example. But these phenomena can't be quite cast in the form of predictions about what happens to physical objects in space and time. So, for example, natural selection and the theory of evolution is really not about predicting that, say, something like an elephant will pop up at some point along the trajectory of our universe, but it's about explaining that life is possible, can arise from very simple elementary beginnings without there being any designer out there constructing objects that are so complex as some of the living beings that we can see around here are. And likewise, there are other phenomena like the properties of quantum and classical information, work and heat in thermodynamics, and which are important for engines like those that I represented here on this slide. So these properties are, again, compatible with the description in terms of microscopic laws of motion of particles, but they are not really about what happens. So, for example, take a bit. When you say that an object is a bit, you're not telling a story about what happens to this object, but you're saying it's an object that can be in one state, 0, and it can be in another state, 1. And these two states can also be copied onto other objects. So these properties are all about what is possible and what is impossible and why. So they're not laws of motion. They are different kinds of things. So the thing that's in common to all of these phenomena I mentioned is precisely this fact that their essence isn't about what occurs to them, so given some initial conditions, which is the actual, that's the stuff that laws of motion describe, but their essence is captured by what could or could not be made to happen on these objects. And these things, these facts about what could or could not be made to happen, are called in general counterfactuals. because they are not actual things, but they are things that you can contemplate by thinking about different possible initial conditions for your object under different possible laws. So here is an idea. Let's try to see whether there are some properties which can only be expressed in terms of counterfactuals, and it's actually hopeless to try to express them with dynamical laws of motion. And I'll give you an example from chess. So there are some facts, like the fact that it's impossible to move into a checkmate from certain configurations, which can only be explained properly in terms of counterfactuals. So this is the example. You see here, there is a king on one side, and on the right we have a king and a horse. Now the knight can move in some places, and likewise the king can also move in only in some places. And so if I were to ask you, why is it that from this position there are no allowed moves that bring me to a checkmate? You could answer in a number of ways, but I think mostly you can think of two ways. One is what I just said. So you could say, well, the king has only certain allowed moves, so only some transformations are possible on the king, and likewise for the knight. And this is why, no matter what you do with these pieces, you won't be able to force a checkmate. But there's another way of answering, and this would be the traditional physics way of answering the question. So something like, well, if we now take the initial conditions of the universe and work out all the allowed positions for the atoms in the brains of the people who are playing this game of chess, given that these brains are programmed with the rules of chess, we will see in the end that there's no way for these two players to end up with one of them checkmating the other. Now, this second explanation is certainly true. I mean, it's true that the particles in the brains of the players obey the laws of motion, but it's not the right answer. It doesn't explain properly what's going on. And the only answer that explains things properly is the answer in terms of counterfactuals, in terms of the statements about what the pieces can or cannot do. And so I want to generalize this idea, which is given for a very simple example, to actually the whole of physics, and explain that these phenomena I mentioned earlier, the physics of life, information, thermodynamics, and even the physics of constructors, can only be captured adequately if we use counterfactuals, and they cannot be expressed solely in terms of initial conditions and laws of motion, which is the traditional paradigm that physics has been using so far. And to help me make this point, I will harness physical principles that already exist. So this idea of using counterfactuals to explain physics isn't new. We know a number of principles that already exist that use counterfactuals. For example, consider the conservation of energy. So, conservation of energy says that a perpetual motion machine is impossible. So it doesn't say that there is a trajectory that has to obey some properties. The most general way of formulating the conservation of energy is really to say that some machines are impossible, no matter what the initial conditions are and no matter what the laws of physics are. Likewise, the second law says it's impossible to convert all heat into useful work. And this is why, unfortunately, when we have dissipation in a system like a spinning wheel, this wheel will at some point come to a stop, and we won't be able to retrieve the energy back in order to put the wheel back into motion. And so that's another kind of impossibility. It's another counterfactual. And finally, Quantum theory also is based on counterfactuals, and this is obvious when you consider the Heisenberg's uncertainty principle. So the Heisenberg uncertainty principle says that it is impossible to copy reliably all states of the simplest quantum system you can think of, which is a qubit, which is the quantum generalization of a bit. And you might have heard this principle formulated in a different form, which is the fact that if you consider an electron, for example, which is a quantum particle, not all of its properties can be measured simultaneously to the same accuracy. So, for example, if you have in perfect focus the electron's position, you can't have in perfect focus its momentum or velocity, and vice versa. And now if you think of a discretized version of the electron as a qubit, for example, the electron's spin, you will see that it too has properties of this kind, which can be jointly used in order to contain information. And that's the fundamental content of the Heisenberg's uncertainty principle. And the fact that they can be jointly used to embody information can be also said in this way that I wrote on the slide, that you can't copy reliably all of the properties of the electron, or in the case of the spin of a qubit. So you see, there are lots of counterfactuals already in physics. And so you can see that these principles that I mentioned are all about what's possible and what's impossible, rather than about particular laws of motion and initial conditions. So the question now is, could we use this counterfactual-based approach to physical principles to generalize its focus and actually cover the whole of physics, not just these few instances that I mentioned here? Could we cover, for example, the physics of living systems? Could we cover the physics of objects that may or may not obey quantum theory, like gravity, for example? And this is the question that motivates this program that in the title of the talk I call the physics of Ken and Kant, but in jargon is called constructor theory. So constructor theory is takes its name from von Neumann's universal constructor, and it should be an upgrade of the theory of quantum computation to cover constructors. And its basic tenet is that fundamental laws should be expressed not as laws of motion, but as principles about what transformations are possible, what transformations are impossible, and why. And the laws of motion, as well as the initial conditions, should actually be not thrown away, not at all, but they should be supplemented by these principles. And so, in a way, emerge out of the principles themselves, and somehow, together with the principles, this should provide a more complete picture of physical reality that can help physics move forward and tackle some problems that currently haven't been solved. So in a way, the way in which you can think of constructor theory or the physics of Ken and Kant is that it's got really two roles. So the first role is that it wants to expand on the quantum theory of computation in a way that ultimately delivers the theory of the universal constructor. And I think this is the way in which David Deutsch, who was this quantum computing pioneer, first conceived of the foundations of this theory back in 2011. But also, it provides new physical principles, and that's also very interesting, that can help us understand the behavior of systems which are not currently completely described by the dynamical laws that we have. In that these principles should be so general that they hold, for example, both for quantum and classical information, and they could also underlie thermodynamics and the physics of life. So in this sense, these principles should be very far-reaching and allow us to make predictions in domains where currently we can't quite use the laws of motion that we have to make predictions, either because they don't hold because of the scales, or they are intractable, it's very hard to apply them, even if they in principle apply, or because these systems that I'm talking about may actually not be described by either general relativity or quantum theory. They may actually elude both. And this is actually the case of gravity. So let me go to the second phase of this talk, where I want to give you an example of where these new counterfactual principles actually make a difference. And this is an example from a recent piece of work that I've been also working on with a number of other people. So the idea here is, can we actually have testable consequences from these new counterfactual principles? Because after all, when you put forward a new theory, yes, you'd like it to provide better foundations for your view of physical reality, but ultimately it would be important to have a handle on experimental consequences, because that's how we test laws, and that's how we make progress, by finding mistakes in existing laws. Okay, so to understand this example that I want to give you, we need a little background. And we will use a very famous tool in quantum physics, which is the tool of a thought experiment. And here's a little cartoon to kind of break the monotony of the talk, which I find quite cute, because it refers to this very well-known thought experiment that Schrödinger put forward to understand the implications of quantum theory when it's applied to a cat, macroscopic object. Luckily, he didn't actually perform the experiment, because the cat actually ends up in a state where it's half alive and half dead, and that's probably not very nice for the cat. However, because quantum theory has, reversible laws, it's all fine, Schrödinger would say, because you can actually undo the experiment and go back to the case where the cat is actually fully alive. But never mind that. So I'm just saying this because I want to say that we are going to perform to perform a thought experiment, and this is nice because even though it's still at the level of an in principle experiment, it can in principle be realized, and that's quite exciting. So the ingredient one for the experiment is the concept of entanglement. Now here it is a kind of complicated scheme where there are two particles being emitted by a source, like two photons, and there are some detectors that are checking their properties. But you don't really need to know much about entanglement other than the fact that it's a special kind of correlation. So when in physics, when we want to describe the fact that a pair or a number of different objects have a property that somehow makes them all similar in certain respects, we use the concept of a correlation. And so, for example, when you want to describe socks, you can say, well, pairs of socks usually come in pairs that have the same color. And the concept of having the same color is one kind of correlation. Now, in quantum systems, you can get kinds of correlations that are actually only quantum mechanical. And entanglement, which hints to the idea of inseparability and so on, is one kind of quantum correlation that only quantum systems can have. So it's a signature of obeying the laws of quantum theory. So that's one thing that the only thing you have to know about entanglement to follow the rest of the talk. The second thing we need to introduce is a problem we have with gravity. Now, as I said earlier, we know that general relativity is the best theory that we have at the moment to describe gravity. It's supposed to be universal, so it applies to anything that has a mass or that has energy in the universe, which includes quantum particles. And this is the problem, because gravity, according to the theory of Einstein, the theory of general relativity, shouldn't have quantum features. So it should be completely classical, plain classical stuff like good old Newtonian mechanics. It's just that it's not like Newtonian mechanics because it's general relativity. But in terms of quantum effects, both general relativity as well as special relativity, as well as Newtonian mechanics, have zero. There are no quantum effects, there's no entanglement, nothing like that. But this is a problem because, of course, quantum particles like electrons have a mass. And that means that then they must interact somehow gravitationally with the gravitational field. So they must have a way of being described by the theory of gravity that we have. But the theory of gravity that we have is classical. And so we end up with a problem. The problem is what happens to the gravitational field when a mass, like an electron, is in a quantum state. So it has quantum features. For example, it's in a superposition of two different locations, like in this pictorial representation. What does the gravitational field do then? Well, there are two answers. And this was already noticed by the founding fathers of quantum theory and GR. Of course, gravity could become quantum, and that's quantum gravity. Or the quantum mass becomes classical. So that would mean that quantum effects are not all powerful after all. And there could be a very strong limitation as to where they apply. So basically, wherever there is something that is where gravitational effects are important, in the case of answer number 2, we expect that quantum effects can be detected or they can't even arise. So you see, this is quite of an embarrassing state of affairs, and it's very embarrassing. It's been around since, now for almost a century. And I think, in a way, being a theoretical physicist, I feel a bit concerned about this. To be fair, there have been very many attempts to actually solve this problem. So people have tried to put together quantum theory and general relativity into what we call quantum gravity. But there is a problem with all of these approaches. The problem is that it's hard to test their consequences. And this was already pointed out by Feynman. So Feynman said, well, can we just resolve this problem about is gravity quantum or not with an experimental test? Should be simple, no? We can, after all, measure quantum features of light, photons and so on. Why can't we just, create a mass which is in a quantum state, make it interact with gravity, let something happen, and then make a measurement on both the mass and the gravitational field? Why can we not test that gravity is quantum if it's quantum? And if it's not, then we see that it's not. Well, it's not as simple as that, because unfortunately, the gravitational interaction is very weak. And so all the quantum gravity proposals that have been suggested so far suggest that these quantum effects, yes, they are there, but it's very, very hard to tease them out of gravity. So we haven't been able to come up so far with a viable, realistic test that can allow us to test quantum effects in gravity. And that's why we can't confirm quantum gravity, and that's why we're still stuck in this very embarrassing position. Now, here's the good piece of news. We think that actually this approach with counterfactuals, with general principles, can help us here. And that is very, very exciting, because here is where you really need something that goes beyond dynamical laws. Why? Because, well, all the dynamical laws that we have, all the laws of motion that we proposed, are not quite able to describe this state where there is a quantum system in a superposition that interacts with gravity. And we need some robust way of making predictions, which is general, more general than any particular laws of motion. And you can see that the logic of principles based on counterfactuals is ideal in this case, because it's exactly like with thermodynamics. When we say the second law predicts this or that, we don't really care about the details of the dynamical equations of the particles that are supposed to obey the second law. We just use the second law. And likewise in this case, could we use these counterfactual principles that constructor theory has to make a prediction in this particular case to test quantum effects in gravity? And the answer is, surprisingly, is that we can. So this is very recent development. So the idea is to use what in jargon is called gravitational entanglement to test quantum effects in gravity. And the striking prediction that we're using to perform, to set up this test comes from general constructor theoretic principles. And they are principles about information. So the prediction is this, that the prediction is that if gravity can create entanglement between two quantum masses, so there are two quantum masses and gravity, and if gravity is able to create entanglement between the two, then gravity must have some quantum feature. This is a bit subtle, so we are trying to say that if we can create entanglement, so this special kind of quantum correlations between two quantum masses, only interacting through gravity, then by measuring the entanglement on the masses, we can confirm that gravity must have some quantum features. We don't really know whether it obeys quantum theory, but it has to have some non-classical features, something that is along the lines of being capable of being in a quantum superposition. And this is very exciting because this would allow us to solve Feynman's problem. So trying to, we would be able to somehow test whether gravity has quantum features simply by measuring the entanglement that is created between two quantum masses through gravity itself. So it's like testing the features of a channel gravity by checking what are the counterfactual properties of the channel. So what are the types of correlations that it can induce in two objects that we're using as probes. Okay, this is greatly exciting. And it's very exciting to the point that actually after Vlatko Vedral and I proposed this, and also another team in London proposed this, led by Sugato Bose, lots of there was a flurry of you know kind of titles of this kind, and lots of, most importantly, colleagues who actually took seriously this idea. So at the moment, this is at the level of a thought experiment, but what we are really hoping is that we'll be able to actually implement this experiment in real life. And it's exciting because the technology we have is quite close to implementing this. And this would also test these constructor theoretic counterfactual principles, specifically the principles about information that are needed in order to make this general claim about the fact that testing the presence of entanglement generating through a channel shows that the channel has to be quantum. Okay, so the most exciting part of this is that if we were able to actually perform this experiment in the lab, we would be able to actually refute all classical theories of gravity, including Einstein's general relativity. So that would be like a momentous step, in the sense that then we would know that these very important theoretical steps that we made in quantum gravity are really, really necessary, because we want to nail this quantum theory of gravity, because we know that gravity actually is quantum. Okay, so you might ask, how far are we from this, from realizing the experiment? Well, we are not that far. Now, you know, we physicists, theoretical physicists, tend to be very optimistic. I think this is, you know, theoretical physicists are always very happy with thought experiments, and then when you go into the lab, the experimentalists pull their hairs out because they start saying, oh my God, this is extremely hard to implement in practice. So the experiment itself is hard to implement in practice, but there are very hopeful signs, and I try to represent them here on this line. You see, on the left, very you can, on the left of this, extreme left of this diagram, this line, there is the electron. I haven't reported it here, but I think you should have written something like, the electron is a very light particle, and we know it has something like 10 to minus 31 kilograms. its mass, and it's a very easy particle to put into quantum superpositions, which is what we need to do in order to perform the experiment. But the electron's mass is too little, too small. We need a larger mass. So then you go along this line and you see buckyballs. Buckyballs are very interesting carbon-based molecules that look like footballs, and they are quite massive, I mean, by microscopic standards, of course, but they're not quite sufficiently massive. Then you move along and you see viruses. So you see coronavirus, for example, it's got that mass. And I've got some colleagues in Vienna who are actually trying to superpose the virus, put it into a quantum state right now. They're actually planning a sort of revenge on corona, trying to put corona in a kind of quantum lab and put it into quantum superpositions. But viruses are too light still. So the mass we need is around 10 to minus 12 kilograms, which is the mass of a human cell. So in a way, it's quite nice because it's much less than 4 kilograms, which is Schrödinger's cat mass, which we know it's very hard to put a cat into a quantum superposition. But it's quite a nice mass because it's not too large, and it's very close to the current experimental capabilities, which are just a few orders of magnitude below this. So this is a very interesting fact, and this is where we are. So we are hoping to be able actually to implement this experiment, and I think this would be very interesting thing to do for a number of reasons, not just because of corroborating the idea that quantum gravity is needed, but also because it would be a first indirect test of these principles that are based on counterfactuals. And also, this would be, in a sense, if people were to implement this experiment, this would be the first example of a quantum computation that goes beyond quantum theory, because whatever is the theory that describes this joint system of quantum mass plus gravity, the exact theory will not be quantum theory as we know it. So it will be a different theory. And so this would be an example of quantum computation that goes beyond quantum theory. So it would be like the first step towards generalizing quantum theory beyond quantum computation beyond quantum theory itself. And we are hoping also that it's like the first step towards this general theory of the universal constructor, of which I hope I managed to give you an overview tonight. And so with this kind of positive, uplifting note, I'll just stop here and thank you for listening, and I'm very happy to take questions.
Hello again, Chiara. Thank you very much for that. It was really interesting talk. Okay, so we've got a few questions coming through, but please keep posting them and I will I'll pass them on. So I have first question here is directly on, I think, on this topic of testing gravitational entanglement. Is how can you, if you do one of these experiments, how can you be sure that it is a gravitational effect that's causing the entanglement? How does that work?
That is a great question. I think the challenge in the experiment is exactly to rule out all other possible interactions between these two quantum masses, and this is extremely hard because there are two ways of doing that. One is that you can shield things like electromagnetic interactions, so you can put some appropriate shields around these masses so that they only interact through gravity. Or you could also be able to, you might be able to discriminate the type of entanglement, because the gravitational force and some of the electrostatic forces have a different behavior at the kind of, so in a way you might be able to see different types of entanglement and differentiate between these different types. But of course, the second way is very hard because gravity is a weak force. So in a sense, it's very important. I mean, the best way would be to isolate the masses, and of course, it's very challenging. But I think in a way, this is already a challenge that people who are doing this interferometry of macroscopic quantum objects are facing. So I believe that, by waiting for long enough, the progress in quantum metrology as well as the progress in quantum computing will allow us to get to the technology where we can do that. So in the sense, I'm optimistic about it, but it's hard.
Okay.
It's very hard.
So you kind of touched on this, but I have another question similar. Of what is it that's currently limiting? This may be a question for the experimentalist rather than you, but what are the current things that are limiting us? So the team who are trying to superimpose a virus, what are they fighting against to get there?
Oh well, I think the difficulty there is so it's basically the fact that these quantum effects are extremely fragile. So you can imagine the key idea with an interferometry experiment is that you want to keep the particle while it's kind of being superposed in such a state that can be reversed. So you want the dynamics of the particle to be reversible. What does that mean? It means that ideally you should only have that particle and nothing else. So the particle should be completely isolated from other stuff. Why? Because as soon as the particle starts interacting with a muon flying by or a photon or whatever, these collisions, if you like, they're quantum collisions, but let's say classically even, mean that the particle gets slightly perturbed, and then you lose this ability of reversing the dynamics, which is key for the interference. And so the challenges are really to do with noise, thermal noise, electromagnetic interactions. The labs in Vienna are massively isolated from, the trams that are going around in town and so on. So you really have to reach a very, very high degree of isolation. And this requires just a lot of money, ultimately, I guess, and, lots of resources being thrown into various technologies that allow you to reduce these noise sources. And this is the same problem that quantum computers have. So it's a similar problem there. But they are getting there for the virus. I don't think corona is kind of like quite a chubby, massive virus, but I think like lighter viruses, the group in Vienna is they're getting there. So I'm really hopeful.
Okay, just to clarify, someone has asked a question about this, but they're not going to help us combat coronavirus. They're just trying to do some physics with with viruses.
Yeah, I think they're just playing safely with some viruses that are actually well behaved. I don't think they're actually trying with corona, but they were planning on trying, a revenge once we are completely got him under control. Yeah.
Okay, good. Okay, so a question from me on this is, if someone does this experiment, what do you think the result will be? Do you think that we will see that there is quantum effects in gravity, or do you think that we'll see that there are no quantum effects in gravity?
So again, my expectation is that we will see that, and I think it's not just. I think most quantum theoreticians would agree with this. I have to say that there are some theoreticians who actually predict the opposite. So, for example, Roger Penrose has a view that beyond a certain scale, quantum effects tend to fade away, and this is largely because of gravity. Exactly. So his prediction would be that we would see no entanglement. And however, let me also say that if we don't see entanglement in this experiment, it doesn't mean that gravity isn't quantum. It just might mean that we are really lousy. We're not very good experimentalists. Okay. We didn't try hard enough.
Yeah. So it could prove it one way, but it doesn't.
Exactly. Nice question.
Falsify the other way. Yeah. Okay.
Precisely. Yeah. That's it. Yes.
Okay. Still a get out of jail free card then. Good. And so I have a question here. Okay. So if let's say this is successful and you show that there's a quantum effect to gravity, does that get us closer to a grand unified theory of everything? Doing that.
I think it does in the form of. So I mean, my view about. Okay, let me just say that about the theory of everything. I always think that that's more like a unicorn in the sense of it's like a mythical entity that somehow we refer to, knowing full well that actually it doesn't really exist, in the sense that if, you know, in a sense, if the physics enterprise is unbounded, which is the way I think about it, other people think differently, but let's say if that's how you think of physics, then even the most accurate theory at one point will have a better version of it somewhere in the future. So somehow I'm always thinking the theory of everything is something that we might attain in a very, very, you know, distant limit, but then after that we'll still be able to get something more in the theory. So it's always like a theory of almost everything in a sense. And in that, you know, if we take it in that sense, I think there is still quite a very big controversy about you know, whether quantum theory actually applies to everything. So whether this quantum effect can exist in anything, in any object in the universe. So showing that gravity must have some quantum features is very important, because it is a step forward towards the unification of our understanding of physics. Otherwise, we would be stuck with this view that there is like a quantum realm and the classical realm of gravity, and we can't quite reconcile them with each other. And I think this is something that physicists are a bit concerned about, to the point that, as I said, some physicists like me think quantum theory is universal and applies to everything. Others, like Penrose and other people, would, on the other hand, prefer quantum theory were not quite true, and that the ultimate reality is actually classical. But we don't like this thing of there's a realm that's classical and one is quantum, because it feels like, you know, there's a needless split of reality into two things, and they are disconnected. But we like unifications. So this would be an important step, I think.
Okay, and so just a question. So if you do this splitting experiment with quantum gravity, the fact that the strength of gravity is very low, presumably is part of the thing. Does this make that, you know, hundreds of times harder than doing an experiment with electromagnetism or something?
That is a very nice question. I think yes, and that's why we need relatively large masses. So I didn't say that the mass we need is something like 10 to minus 12 kilograms. The mass where that's important for quantum gravity is this mass called Planck's mass, which is 10 to minus 8 kilograms. So the mass we need is not quite as large as Planck's mass, but it's quite close to that boundary. And that is what makes the experiment challenging, because the mass is large, relatively large. Now with charges, these effects are actually within reach of experimental realization. So in a way, you could actually, we already know that the electromagnetic field is quantum, but we could, for example, just for fun, take two charges, put them into quantum superpositions, entangle them through light, through electromagnetic interaction, photons, and then conclude that photons are quantum. So this could be an indirect way of showing. So if you think of all the times where we are entangling two charges through electromagnetic interaction, that, according to this argument that I mentioned, that's an indirect way of showing that the electromagnetic field is quantum as well. So it's a great question, and I think there is no one has done this experiment yet. I mean, it's doable now, but I think no one has actually tried with two charges. So that would be kind of a nice thing to do too.
Okay, I have a question here, which is probably a whole talk in itself, but I'll ask it. How does a quantum computer work, and what's the application? What are applications?
Sorry, I didn't catch the start.
Sorry, okay, how does a quantum computer work, and what would their applications be?
Okay, so the quantum computer works exactly in some sense, it works exactly in the same way that the computer we're using now works. So it has it needs programs, so you have to input some programs in it, and the programs say which gates or elementary steps you have to perform in order to solve to perform a certain overall computation. And so the architecture is largely the same. It's just that each of these steps, instead of being, a NOT gate or an AND gate and so on, which are classical, each of them is implemented by the Schrödinger equation, basically. So it's powered by these different laws that quantum objects obey. Now, of course, it's not to say that the electrons in the transistors inside our computers are not quantum. Of course, they are quantum. But the point is that the logic we are using when we have, transistor off, transistor on, and so on, that's all classical. Whereas in the quantum computer, the logic is quantum in the form that the elementary units of information are not bits, but they are quantum systems. They are qubits. And a qubit is like it's a system that can be that has a multiplicity of ways of embodying a bit. So it's not just 0 and 1 in one sense. It's 0 and 1 in multiple ways. And I think when you perform a quantum computation, you're using this fact that because the qubit can be in a superposition of both 0 and 1, you can somehow parallel process and check the result of a classical computation along multiple paths. And that's somehow, and by analogy, it's one of the reasons why you get this quantum advantage of speed up. So most applications of quantum computing are about speeding up the algorithms that to perform given computations. And one major application was factoring, the problem of factoring a number into factors. So I give you 15 and you've got to find 3 and 5 as factors. That's very simple, but let's say, supposing you want to do it for a very large number, that's this very hard problem that takes the age of the universe to solve for a classical computer. But for a quantum computer, it can be done in finite time. And the other kind of application, which doesn't require a universal quantum computer, so one that can be programmed to do anything, is quantum cryptography. So cryptography is this general set of procedures to protect information. So you can somehow hide information in a way that eavesdroppers can't get to it. And quantum technologies allow you to do this in a way that's super secure, and it's based on entanglement or other quantum effects. So these are the two major applications of quantum computing. And quantum cryptography, unlike the others that I mentioned, doesn't require a fully fledged universal quantum computer, and it can be realized even with kind of standalone type of realizations. So I think quantum computing will actually lead to a massive revolution when it's around. So kind of we're waiting for that.
Okay, with bated breath. Okay, so we're nearly 8 o'clock now. So I'll just I'll give a couple more questions to you, and then we'll finish up. I've got loads here. I'm just trying to pick ones which are kind of popular type questions to ask. So this is, I think this is an interesting one. Does this approach have anything to say about the possibility of a multiverse or a single universe?
That is a very nice question. So I think the physics of counterfactual doesn't necessarily so it holds for single universe theories too. So it would hold for a theory where, like classical physics, where there is a single one universe that doesn't have different branches and so on, in the sense of the quantum multiverse. However, when you introduce some principles that are about quantum information, so not the classical information that classical systems can embody, but quantum information type principles. Those principles, if you look at how they work, etc., even though they don't mention the fact that there has to be a multiverse, they are only compatible with the fully fledged quantum theory that we know. And the point is that there is no way to round it, that if you take quantum theory seriously, so you don't try to change it in the way that you add something like collapse of the wave function or something like that, which is a different theory. But if you just take quantum theory seriously and you apply it to the whole universe, unfortunately, there's no way of escaping the conclusion that if you think that that's the way in which the universe is described, there must be a multiverse. And it's not as bad in the sense that this is as mind-boggling, let's say, as GR, because GR also, when taken seriously, says that there must be some such thing as space-time. And space-time is actually quite a hard thing to picture in your head. The multiverse is similar, and the approach with counterfactuals kind of helps making sense of it in a way that allows us to see that the presence of a classical world inside the multiverse is perfectly consistent with the fact that we think that the real universe is actually out there in the form of different branches of the wave function. So in that sense, I think the short answer is that the principles are compatible with both a single universe or a many universe theory, but as soon as you insert the possibility of quantum information, then you got to go with the multiverse view of quantum theory itself.
Okay, thank you. I think I followed that. Okay, so I think we'll wrap up there. I'm just going to do the last question myself.
Yeah, please.
But before I do, because you've been very restrained, there are lots of questions here, and I will tell lots of people who've asked the questions. Chiara has a book called The Science of Can and Can't, which I've read and is brilliant. So read that first, and if you still haven't got an answer, come back to us for the ones we haven't.
Yeah, thank you.
Haven't found.
And to write emails as well. You can find my email online, and very happy to reply to questions as well if you can't ask them now.
Yeah, thank you. So I think mine was from the talk and from reading your book. The approach that you have is obviously using the counterfactuals is not the traditional approach to physics, which you kind of talked about. How do you feel that is kind of received by the establishment of physics? Is it something that people are kind of warming up to, or are people suspicious of this, or?
Well, it depends. I guess I have some very close collaborators that I've mentioned in the talk and so on, and I think obviously those are very, students and postdocs and so on. So all of the community around me is very happy with applying these things. The rest of the community has quite liked these ideas that are behind this proposal I mentioned and others. And I think they are just waiting in the form of, is this going to solve really all of these problems? And I think it's like a warm skepticism, which I kind of like, because I guess it's the best type of response you can hope for. In the sense that it's quite right. I think we physicists like to be pragmatic. So when someone comes up with something new, which in this case is not as new, as I said, because it's in the tradition of these principles. So in a sense, it's not that unfamiliar, hopefully. Mm-hmm. But let's say if someone comes up with something new, it's always like, okay, so how can we use this to solve problems? And I think that's what I've been trying to do myself when I kind of stumbled upon this proposal that David Deutsch made when I was a student back then in Oxford. I think the challenge there was to try to find a few tractable problems where this approach could make a difference. And I think that we've done, and now we want to do more. And I think so. My hope is that there'll be more and more growing interest on this already kind of growing momentum. So I think it's looking nicely at the moment. So I'm hoping for kind of this to be something useful for physics.
Okay, thank you very much. I hope so too. So I think we'll draw to a close there. Thanks very much to Chiara for the talk tonight and for answering the questions. Thank you to everyone who listened in and posted your questions. And I'm sorry we couldn't get through all of them. That's it for tonight. So thank you.
Yeah, thank you very much for having me. It's great.
Okay.
Thank you. Bye.
Bye.